All right, thank you. Everybody, come on in and sit down and let's get going again. Listen, it's a real pleasure to be moderating this panel. We have the home team here. You can't come to Boulder and not hear from NREL, the National Renewable Energies Lab, and we're just so pleased that Steve Hammond and a couple of his colleagues are here today. We thought it would just be a terrific idea to have them participate and give us an update on some of the real cutting-edge computational work that's underway here. As a number of you know, NREL has one of the newer supercomputer centers in the DOE system, and Steve Hammond, who will be speaking first, is the head of that supercomputing center. Also joining him is Mike Sprague, who is a senior scientist in the center also. His research interests include computational mechanics of fluids and structures and numerical methods for modeling. And then also Vlad Stevanovic is a senior scientist, but in the Material Science Center here at NREL. And he's also an assistant professor at the Metallurgical and Materials Engineering Department at Colorado School of Mines. So we have a full Colorado contingency here, and we look forward to hearing from you guys about what's going on. Steve, do you want to kick it off?
Thank you, Susie. So I want to thank IDC and the organizers for inviting us to speak. It is a pleasure going to a meeting and having it as a home game. I think it's 15 minutes from my garage to the parking lot here. It's closer than getting to the lab. And so when I spoke at this meeting a year ago in Seattle, and I talked about our data center, talked about our energy efficiency and our what we were doing. And so I wanted to elaborate a bit on how we operate the center, our role, where we sit in the DOE complex. And so I'm going to give sort of a broad brush of the types of applications that we're supporting. And I'm going to turn it over to Mike and to Vlad to talk about research in modeling the flow physics of whole wind plants. So that's a capability type of problem. And then Vlad for a material science, which is more of an ensemble and a capacity kind of application. See if this goes. There. So I'm guessing most know the structure of the Department of Energy as it pertains to the upper left portion, right? So there's NNSA, which is the full left part of the org chart. The Office of Science and Energy under Deputy Secretary Lynn Orr. The first box under there is the Office of Science. If you go 2 boxes below that, highlighted in red, I'm not sure, you probably can't see the eye chart. So that's the Office of Energy Efficiency and Renewable Energy. There's also Environmental Management. So there's a number of energy offices under Lynn Orr. So we're our sponsor, our primary sponsor is the Office of Energy Efficiency and Renewable Energy, and it's a sister office, if you will, or companion office to the Office of Science. So the Office of Energy Efficiency and Renewable Energy has 11 offices within it, much like Office of Science has basic energy research, or basic energy sciences, biological and environmental research, and fusion, high energy physics, and nuclear physics. The ERE offices span 3 directorates from renewable power to energy efficiency to sustainable transportation, and that includes solar, geothermal, wind, and water. In the efficiency side, it's homes, buildings, advanced manufacturing, government energy management, which looks at improving the efficiency of buildings within the government complex. And then you'd imagine in transportation, there's vehicles, fuels, and hydrogen and fuel cells. So when we look at the DOE portfolio of computing, most of the focus to the meeting to date has been at the sort of tip of the spear, the leading edge systems driven by Office of Science and NSA. There's also lots of institutional computing systems sort of sitting in there, and I think it's been mentioned there's a sort of a missing middle. And looking at HPC resources for the energy offices, something that's maybe 10% of the leadership class system. And it's not just hardware, but what ERE is looking to do is to establish computational science, modeling, and simulation as a means for advancing their mission, just as the Office of Science and NSA has done for theirs over the past decades. So we're relatively newer, but the focus is on sort of developing a culture of high-performance computing and modeling and simulation for the energy offices and to fill a gap that's not being met at the leadership class system. So it's not just hardware, but there's expertise, there's domain expertise in doing something that's indigenous at the other labs and offices. So our role, the mandate is, we are at NREL, we provide the primary facility for the Office of Energy Efficiency and Renewable Energy for providing high-performance computing. The system we have, which is a 1.2 petaflop system, is the largest system in the world dedicated to renewable energy and energy efficiency. Go on. So we are EERE's only laboratory. Compared to NSF and the other parts of DOE, we're relatively new to large-scale computing for advancing the mission. We're in the process of working with EER leadership on defining long-term HPC strategy and a stewardship plan. Our objectives are to meet the computational needs of EERE-funded projects, independent of where that work is conducted. So EERE actually has projects at most of the labs in the lab complex, as well as universities, and they provide support to industry. So whether that work is at NREL or at the other labs, we're positioned to support that work. We're looking to advance scientific discovery and have impact, to develop and nurture a culture of computational sciences for the breadth of the EERE mission and establish productive and efficient facilities to support the computational capabilities. If you were at the meeting last year, we talked about our high-performance computing data center. We have a brand new 182,000 square foot research facility. The data center sits in the middle, indicated with the orange arrow. So we have 10,000 square feet of usable uninterrupted floor space. That's our raised floor. It's a 10 megawatt capable facility. It's a LEED platinum facility, and we've operated for the last year and a half. Our running average at PUE is below 1.06, so we're very efficient. We use evaporative cooling only. We take advantage of our dry, cool nights. So we were able to build this at a lower cost than if we had built a less efficient, if we were using mechanical chillers, and our operating expenses are much lower relative to other data centers. We've driven direct component level liquid cooling, so our cooling supply is 75 Fahrenheit water. We get 110 Fahrenheit degree water back, so we do waste heat capture and reuse, so it's a primary heat source for our full laboratory building. We have a few fans, but mostly it's pumps, and pumps are much more efficient for cooling than lots of fans. We've adopted a holistic view of the data center from chips to bricks, and so we've integrated our compute capability into the data center and the data center into the campus. And we're actually, over the summer, we were exporting heat from outside of our building to other places on campus. So part of that was our data center mission, so we're advancing energy efficiency. We're looking ahead towards much larger systems, and if you're not paying attention to efficiency, your operating costs can exceed your capital costs for acquiring your systems. And if you're looking at an exascale system with 20 megawatts, you're going to pay probably $1 million a megawatt year to operate that system. And if you're not efficiently powering and cooling it, the millions of dollars start to add up very significantly. So beyond power usage effectiveness, we're also looking at water usage, advancing liquid cooling and energy efficiency, looking at reducing carbon footprint in the computing enterprise, advancing waste heat capture and reuse, and also energy management, demand response, and shifting loads. How do we do that within a quality of service agreement with our applications? So we go through an annual allocation process. We're in the midst of reviewing and allocating our system for the FY16 year. It's modeled somewhat after the ALCC process conducted by the Office of Science, but it's driven by EERE programmatic milestones. So let me see. So we're ensuring our resources are aligned with the mission. So people who are requesting time, we want to make sure that's aligned with projects that are funded within the Office of Energy Efficiency and Renewable Energy. So that's aligned with milestones, part of ERE solicitations, and then within the ERE mission space. So our current compute capabilities, our system is called Peregrine. It's a 1.2 petaflop peak. We have 1,440 nodes, mostly Intel Xeon, some Xeon plus Phi nodes. We're in the process of adding another petaflop, so that's 1,152 additional dual socket Xeon nodes are arriving Monday. So we'll have a 2.2 petaflop peak system that'll be available for use starting November 1st. We have Mellanox InfiniBand interconnect. We do have a 3 petabyte Lustre based on DDN file system. We've got a 7 petabyte Sun Oracle Storage Tech. The old Storage Tech facility was just across 36 here. So we've got our tape library. We also have an insight center for immersive, interactive scientific visualization and data analytics to go with this. If you wonder where our projects are, during fiscal year 15, we're supporting 68 projects. The big three, in terms of 75% of our workload, is in wind and water power modeling and simulation, bioenergy applications, and solar energy. We also do work in buildings efficiency, energy systems and grid modernization modeling, some computational science projects, and then vehicles. We have a very mixed workload. We have some traditional capability, large jobs that take a good fraction of the system, but we also have a lot of jobs that do parametric studies. I would say our workloads differ from typical sort of Office of Science workloads in that they're engineering and optimization. I was joking with the Office of Science program manager, and he said, geez, I don't envy you guys. We publish papers, and pardon my French, he says, your shit's got to work, right? So when we're looking at wind turbines and we're looking at PV systems, it's not a existence proof, it's a for all. So they've got to sit in the field and work for 20 years and optimizing the materials in use and over the lifetime of the system in various weathering conditions. So there's a lot of engineering optimizations or finding materials that are earth abundant that give the same sort of optical and electrical properties that are desired are important facets. We do a lot of computational screening and guiding of engineering. These are workloads that aren't necessarily sort of tightly coupled PDE solves of traditional Office of Science workloads. We do a lot of resource assessments. We look at, I'll say a little bit more about that, but looking at where there are wind resources or where there are optimal solar resources during diurnal cycles and different seasons and interannual variability. We also have some jobs that take lots of small node count, but they do hundreds of them, and they need large memory footprint, and they need to run for several days at a shot. Then we have tight coupling with industry. We have over 340 cooperative research and development agreements with industry. So we have proprietary designs and data that we work with, and we can't necessarily just ship that off to a cloud resource somewhere. So taking a look across some of the spectrum of the modeling and simulation that we do, Mike is going to go in a deep dive on this, but shifting from modeling individual blades and turbines to looking at the complex flow physics of whole wind plants is one area that we've identified as a clear exascale application. So I'll let Mike speak to that in depth when he's up. I mentioned resource assessments. So we're responsible for providing assessments for the wind industry and make the data available. So we reanalyze weather data and provide 80-meter tower data across all of the continental US at 5-minute intervals at roughly 1 to 2 kilometer resolution, so that people interested in deploying wind turbines can know where that's going to go, and we do that over 10 years. So I think we've got, this was in collaboration with 3-tier, and the full data set was 500 terabytes that we make available to the wind industry. In fuels, We do a lot of molecular dynamics work, looking at how enzymes can break down cellulose. So this is the woody parts of plants. How do we break down the cellulose? So think of it as like a hardwood floor, and how do you peel up the planks of the hardwood floor with the enzymes and break that down to simple sugars that can then be fermented to make ethanol. So the molecular dynamics use, many thousands of cores at its shot for these, and then they do these as umbrella samples and have, I'm sure if we let them, they would take over our whole system. They're probably our equivalent of the QCD folks. In the vehicles area, there's a lot of interest in lithium-ion batteries from integrated into vehicle systems and looking at the degradation of lithium-ion batteries over frequent charge and discharge cycles and how the materials change. So large-scale compute resources are allowing our folks to look at broader temporal and spatial scales to look at how these materials, how they evolve over time and how the grains of the materials shift and take on different physical characteristics. You may have seen some of the spectacular videos of lithium-ion batteries sort of spontaneously short-circuiting and catching fire. It would be catastrophic if that was in a vehicle. There's a lot of work, and traditional strength of the lab is in electronic structure calculations for materials for photovoltaics, both more accurately prediction of the energy levels for point defects, as well as looking at crystalline structures for improved polycrystalline materials. We're getting close with the supercell size, and the modeling and simulation that we can do is now in close agreement to what we observe experimentally. So larger systems has been a great benefit in looking at improved PV materials. Another, probably our fastest growing area is in grid modernization and energy systems integration. So we use Plexus, which is a unit commitment software. We've analyzed the entire Eastern Interconnect of the US and looked at various scenarios of higher penetrations of wind and PV resources into the grid, and under certain scenarios, how much storage will be needed to maintain grid stability if we were to shift to, say, 30, 40, or 50% renewables in our grid interconnect. One of the last applications I wanted to highlight was geothermal well drilling. There's a small company just outside of Denver that we work with. They're modeling enhanced geothermal well drilling. So they use ANSYS, and they used to do all of their analysis on some workstations, and they've been working with us for the past year or so to study higher pressure and temperatures, and it's been a great turnaround for them as they go forward, looking at geothermal wells and where they can take advantage of some of the oil and gas techniques and use this for geothermal and energy recovery there. I think one of the more satisfying things we've gotten is for a new center, we've actually received some relatively high-profile accolades, both in terms of our efficiency as well as the Editor's Choice Award for achievement in application of HPC for renewable energy. We've received 2 R&D 100 awards for our approach to energy efficient computing in collaboration with HP and Intel, and a DOE Sustainability Award. So I'm going to stop here. I'm going to turn it over to Mike to give a deep dive on wind modeling, and then to Vlad for materials in solar.
Work? Okay, thanks, Steve. Yeah, so as Steve said, I'm going to talk about the modeling work we've been doing, and then DOE more broadly has been doing around wind plant modeling. So I'm going to I put Matt Churchfield's name on here. He works at NREL as well, but he works up at the National Wind Technology Center. I'm going to be showing some of his results, so a lot of the cool things that I can show today are his work. I work in the Computational Science Center, but I do a lot of basically numerical methods for PDEs, a lot of computational mechanics, so I work with the guys up at the wind site quite a bit. The talk today, I really want to talk about, I want to motivate the problem and talk about real opportunities and real challenges that we face trying to do the wind plant problem. I'm going to talk about the wind plant simulation as being a really good exascale problem. Talk about what DOE is doing to support this, and talk a little bit about where we are with the state of the art in wind plant simulation. So where's DOE fit in the whole wind energy spectrum? Okay, if you go out there, you're going to see a lot of really big wind turbines out there, big multi-megawatt turbines out there. I would say, and a lot of people would say, that the industry has really figured it out when it comes to putting up a big turbine out in the middle of a field with no other turbines around it. They feel pretty confident about it. They can predict what it's going to do pretty well, and they have a fair amount of confidence on how long it's going to last, okay? So I don't know that there's a lot we can offer there that they don't already know. But if you're talking about wide-scale deployment and you're trying to make wind power competitive with fossil fuels without subsidies, that means you have to have much greater penetration. That means large wind plants, tens to hundreds or even maybe more wind turbines all in the vicinity, okay? And so there are quite a few challenges that a wind plant will face, or I should say, a turbine that lives in a wind plant will face a lot of challenges that a turbine out in the field by itself will not face. Okay, and that really comes down to the fluid dynamics that are going on in that wind plant. So there's a few numbers up here. So, yeah, oops, I'm new to this, Vladan. Am I going the right way? Yes. There we go. All right. So if you think about scaling up the single turbine in a field by itself, and you say, well, I'm going to have 100 of these, right? You're not going to get 100 times scale up, okay? You're going to look at about 20% losses. And this is basically due to the wake interactions, okay? If you're in complex terrain, it's going to be greater than that, 30%, maybe more. We're not going to be able to get rid of that totally, but we can reduce that, all right? So the wind plant faces a reduction in power output just inherently, that is inherently there, but we can reduce that and we can optimize that, okay? The turbine failure rates are significantly higher in a wind farm. Again, we believe this has to do with the wakes. You're going to see a fatigue loading, if you will, that translates into more frequent bearing failures, gearbox failures, and so forth. And then, again, because the industry is not well equipped to optimize and design an entire wind plant, the tools are not there yet. There's a huge uncertainty when you're designing this plant and you're going to say, okay, well, this is what our power production is going to look like. Okay, there's a huge uncertainty there. And then the expression I love to use that I hear in this part of it is the cost of money, okay? So basically, they want to finance these things, right? And they go to the financiers, and they have a huge amount of uncertainty, okay? And the people who are financing look at that, and they don't like that. So that means cost of money is high. So if the wind industry had the tools to reduce that uncertainty, quantify that uncertainty, that means a reduction in the cost of energy. Okay, so opportunities. So where does HPC, where does wind plant modeling come into this? Again, this is really about reducing the cost of energy and addressing some of the things I was just talking about. The wind plant, again, the flow dynamics in a wind plant are really poorly understood. And I'll talk about that more in a little bit. It's an extremely complicated system. I guess maybe my point here is that if we understood it better, we'd be able to design better plants, all right? And again, I mentioned the tools that the industry has right now for designing wind plants. I would say they're pretty lacking. They're quite low fidelity, and they are not validated for wind plants. And again, they present a huge amount of uncertainty, which then translates into how well they can accommodate design standards. Okay. So here, what I'm really interested in on this bullet is how can we take the results from validated high-fidelity simulation and translate that to better models that are used by the industry. Control systems. Control systems is an interesting one because the control systems, any improvements to the control systems can be applied to wind plants today. All right, what can we do with control systems that will optimize an existing plant? Some of these other advances, well, that's not going to help a wind plant that's already been built. All right, it's not like we can move these turbines around to new places, optimize an existing wind plant. But the control systems, any improvements there can have an immediate benefit on production of an existing wind plant. And of course, reduced uncertainty in predicted plant performance. Again, this comes back to new plants, lower cost of money, and thereby reducing the cost of energy. And this is just one of the wind plant simulations that Matt Churchfield did. I'll talk a little bit more about these, where we are with the state of the art in a little bit. Let's see. Okay, so we got, hopefully I motivated it well enough. There's a lot of opportunities that high-performance computing can bring to the wind problem. And for those of you who are familiar with fluid dynamics, a cascade of scales causes this to be a very problematic problem. All right, there's a huge span of flow scales when you're looking at the wind problem. All right, this diagram tries to illustrate that. Right at the blade surface, you have extremely complicated boundary layer physics, and those play a big role in how that blade performs, which of course plays a role in how the turbine performs. You have the blade boundary layer scale, you have the turbine scale, you have the array scale, and of course, while we may be focused on simulations that encompass the entire wind plant, if you don't have the right boundary conditions for that wind plant box, it is perhaps not a very valuable thing. So you got to bring in at least weather scale data in some capacity to drive your wind plant box. And then if you're really going to think long term, then who knows? Maybe you go out to the climate scale. But this goes from, I think we listed 10 to the minus 5 here for a grid cell spacing, if you're going to capture the boundary layer correctly, and then it goes way out there to climate scales. It depends where you want to go there. The coupling, the two-way coupling varies in its strength on these different scales, but you can see there's a huge span of flow scales that we need to deal with. Okay, let's look at very complicated flow physics that our models have to capture within the wind plant itself. Let's see, I'll call out a few of these. So I just talked about the boundary conditions on your wind plant box, right? So modeling the atmospheric boundary layer in a manner or to a fidelity that is appropriate for a wind plant is not an easy thing in itself. Okay, there are a lot of physics going on in there. You have the atmospheric boundary layer, you have the stability, you can see these little plumes coming off the ground. You have these low-level jets that, with today's turbines, capture the top part of the turbine, no problem. The turbines are so big now, it goes right into that low-level jet, which can cause quite a bit of big shear profile across the rotor diameter. And of course, you have complicated wakes that are going on in the turbines. If you have complex terrain, again, hopefully you're getting the gist of this. This is a really complicated system now that we have to solve within our wind plant box. So just to look at the basic problem overview and some of the things that we use to solve this problem. So it's a multi-scale and multi-physics problem. There's no single model or code that is going to solve this whole spectrum that we need to solve. If you look at the individual components, you could say, okay, mathematical and computational models exist for each of these different components, and some examples are down here. So for example, this is a mesoscale simulation, a numerical weather prediction simulation. That's the WRF code, if you're familiar with that, weather research and forecasting. That's from John Michalakis. This is a single turbine simulation. Again, we feel pretty good in this regime, but there's still tons to be done. That's open foam that Matt Churchfield did. then we have down to the structure. This is a finite element model, and that one's, I think, an ANSYS finite element model that Sandia has made. And just to point out, these blades now, they're huge. They're 50 meters in length. And as they get bigger, they need to become less dense. Okay, you can't just scale up an existing turbine blade. It would be way too heavy. So they become very flexible. So if you go out and look at a large turbine today in a decent amount of wind, you will see these blades flexing dramatically. They will flex, they will twist. There's aeroelastic bend twist coupling that goes on. They're pretty complicated mechanical systems. So you need to couple all these together. So we need rigorous and efficient and scalable coupling of these models. So just to look at some resource requirements, okay? What are we looking at for simulations today, and what are we looking at for where we want to be, okay? The simulation I showed of MATS before uses what are called actuator lines. It basically is a line force that exists in the CFD grid. So the CFD grid can be fixed, and you can have this line force moving through the domain. It's a greatly simplifying thing that makes these simulations accessible. But even so, if you're going to say, as an example, and Matt Churchfield went through these number calculations, but basically let's say we have a 49 turbine wind plant. It's in flat terrain. It's covering 25 kilometers squared. It goes a kilometer into the atmosphere, and you only want to simulate 30 minutes. I won't go into these numbers, but basically, if you're going to simulate 30 minutes, it's going to take about 2 weeks on a leadership class machine. There are a lot of approximations in this approach. There's a lot of questions about how predictive these actuator line simulations are and how good the CFD is with this kind of grid resolution. Looking forward, we want to be able to resolve the surface of the blades to reduce as many of these approximations as we can. If we think about that, so future simulations with resolved turbines, what did he call out? I mean, we're talking billions of grid points here. We're talking million time steps, billion CPU hours. I mean, if you look at the numbers here for the future simulations that we're looking at, we're actually resolving down to the blade surface, the blade geometry. We're very much talking an exascale system problem. What I will say about this for exascale is that the wind plant problem is very well suited because you could see it as a weak scaling problem, okay? If you were going to do the single turbine problem and do the blade resolve single turbine problem in that one box, one turbine, it's a petascale problem. So if we want to do 100 or 1,000 turbines, it's a weak scaling up of those boxes. So this fits within the desired goal of exascale computing of the bigger problems, okay? It is a very nice capability problem. I wanted to say a few words about what the DOE Office of Energy Efficiency and Renewable Energy, how they're looking at this and what they want to do with this. And there's the Atmosphere to Electrons initiative. And over the last year, Steve and I and a lot of other people have been very involved with planning and trying to get this off the ground. And this is pretty exciting for me because it is really a shift for that office. They're really trying to use high-fidelity modeling to understand the fundamental physics of whole wind plants. It's a programmatic shift from looking at single turbines to the whole wind plant. And high-fidelity modeling is a huge part of that. It is at the core of it. They're doing it right in my mind. They are supporting an experimental campaign that is validation directed. So the planning meetings we've had modelers, we've had experimentalists working together to design the experiments. We also have effort of the DAP, a data analysis portal. That's going to be at PNNL. And so the data should be publicly available, both experimental and simulation data is meant to be on the DAP. We've held 2 well-attended workshops for this program since January. We had one workshop where we were just looking at creating the modeling and simulation environment to address the wind plant problem. Had about 60 or 70 people at both of these, and we had another one, the wind plant modeling, and this is where we got experimentalists together. and the modelers together to design the experimental campaign and the models that will be used in the ModSim environment. And for those of you who are into CFD, if you haven't heard of it, we just had an Oscar-led workshop on turbulent flow simulation at the exascale. And that workshop report is coming together now. The website has a bunch of we'll have all the plenary talks and so forth. But for those of you who are into CFD, you might want to take a look at what came out of that. I'll just make a few closing remarks, then I'm going to show a movie. So I'm confident that HPC does offer us a pathway to reducing the cost of energy for wind energy. Capability versus capacity computing. I find this topic to be quite interesting in CFD land. CFD has traditionally been just, the poster child for a capability computing. When you get coming out of the turbulence flow workshop last month, it was very interesting how much, and let me step back and say that was the application, those were all DOE application experts as well as just hardcore computing guys as well. And there was a consistent call out for capacity computing in the exascale for CFD. And this comes down to uncertainty quantification, sensitivity analysis. And in the exascale context, what people were promoting is not just simulations that could have been done with 1,000 petascale systems, but what they would call our loosely coupled, say, optimization, or loosely coupled ensemble simulations. And I was interested to hear a very consistent call for the importance of ensemble calculations in that context, which there's a mismatch then when you come to Oscar, for example, who is very much interested in capability computing. But I'm happy to talk more about that one off the record if someone wants to. We're looking at still some challenges within this research area. So that mesoscale, numerical weather prediction, trying to couple that with our wind farm simulations, that one is still a pretty big unknown on how to do it well. Coupling turbulent flow across scales like that is not a straightforward thing. Uncertainty quantification and sensitivity analysis, we're talking huge simulations here. So what does that look like? Is that even possible? Verification and validation, coupling computation and physical data, data analysis. I mean, these are topics that fit broadly in the exascale environment. Multi-fidelity model management, and then looking very much at how does HPC influence the models that industry is using, so the lower fidelity models that industry is using. Let's see, where are we? So so my colleague Matt Churchfield put together this little presentation about, well, I'll say that this is a demonstration of how HPC can be used to influence an existing wind plant through, for example, a control system modification. Control systems have been traditionally very turbine-centric. So I'm an individual turbine in a wind farm. I want to optimize my own power production. This is a flawed, egocentric view. Okay? This is where you should really be thinking about the whole. And so the example here that Matt's showing, so basically we have 1, 2, 3, 4, 5 wind turbines, and in this case, the wind is going right down the turbine line, okay? And in a turbine-centric point of view, each turbine is going to be facing that prevailing wind direction, okay? The idea is detune, if you will, detune each turbine. You give it a yaw angle off of its preferred angle, and then look at the whole plant performance instead, okay? So the idea is, let's see if that works. I don't know if it's playing. There we go. Okay, so you can see the yaw misalignment. So he's twisting each turbine off the main direction, okay? And I'll just stop it right there and take a look at this. So on the left here, all the turbines are aligned. So this is an open foam simulation with those actuator lines I was talking about. And each turbine, of course, is living in the wake of all the turbines up in front of it. Over here, you can't see it so much here. You'll see it more in a moment, perhaps. These guys are yawed. So each one is is not optimally placed. You can see that the wake kind of goes off to the side there. All right, so you've basically, by taking the yaw some number of degrees off of optimal, you've pushed the wake to the side. There's two plots on the right here. This is the total power produced in the two scenarios. These are aligned turbines. These are with the wake redirection. And there's a small percentage here that is consistently better for the non-optimal individual turbine configuration. The bottom plot is the energy produced by the wind plant as a function of time. So there's a couple things here, right? A small performance increase like this can translate to a huge change in the overall energy capture. Okay, this can make a huge difference in the cost of energy as produced from the plant. And you can see it's a pretty consistent overproduction there. So an example of how if you just change a control system environment, you can make a significant change in the overall power production of the wind plant. I guess I'm going to stop right there. And I'll turn it over to Vladan.
Yeah. Okay, while this thing is setting up, I haven't tried it before, so hopefully it will work. Hello, everyone. As you can see, my name is Vladan Stevanovic, and I'm coming from two institutions, Colorado School of Mines and NREL, that are like 4 miles apart. And my work is more on the fundamental science side than the applied. Per Steve's previous remark, I'm one of those guys that publish papers. But I hope to be doing something that is actually at the same time relevant. And then Steve invited me to talk here about materials by design, which basically is, it stands, I mean, it's a hot phrase, but what it stands for, it's basically, can we design materials like we design cars? Can we assemble atoms in a certain way, knowing the way, and then be able to predict properties and actually realize those materials in reality? And then when I first heard this kind of definition of what materials by design is, I said, okay, so what? I mean, since the Bronze Age, humanity was doing the same thing. I mean, bronze was an alloy that was fabricated for a certain purpose, and then for a certain amount of time it was useful. And it still is. So what is different now than in the Bronze Age is that we now can model using high-performance computing and using quantum mechanics the interactions between the atoms, the interactions between electrons and protons and so forth, and basically predict materials properties. And HPC is a really important part in that. So, okay, motivation is, what this slide shows is the history of materials discovered in 20th century as a function of time. And if you look here, every material that you probably use in your everyday life took from the first paper published on that material until the deployment about 20 plus years. So the idea is, can we use high-performance computing and our knowledge of quantum mechanics to speed up this process? And recognizing this goal, the White House launched the Materials Genome Initiative in 2011, 2012, with the main goal to do materials design twice as fast at half of the cost. So we want to be better, faster, cheaper, everything. And Materials Genome Initiative specifically calls for tight integration between computations and experiment and data. So what is the role, and I'm the computational guy and to some extent data guy. So what is the role in this of the computations and data? And I see three kind of roles. First, we want to have predictive approaches to actually, because of course the reality is more complex than we can model it ever. So the question is, how can we approximate that reality so to be relevant. So I'm sitting in the place where I'm trying to develop predictive models that can be used on high-performance computing machines that can actually produce some results. So there is that part in data generation. Then there is a Materials Genome Initiative called specifically for data sharing and building knowledge from the data. And that applies to both experimental and computational data. A couple of words about MGI work at NREL and Colorado School of Mines. We had a number of programs, and we still have a number of programs, and I'm listing 4. The first one is the Center for Inverse Design. That was a previous Energy Frontiers Research Center funding by the US Department of Energy. It stopped existing last summer, but then we recompeted and we got the new EFRC, which is called Center for Next Generation Materials by Design. And these are large 20 million-ish dollar efforts over 4 to 5 years, involving multiple institutions and NREL as the lead. There is also an NREL MADDB, which is the database listing all the results from these efforts that is hosted by NREL HPC. And then we also have programs which we called TE Design Lab on thermoelectrics funded by the National Science Foundation. Slide on people. These are the people. I will not go. So we have collaborations with MIT, Harvard, and the other institutions involved in these relatively large programs. So what I want to show you here is an example of what I actually do and why are HPC resources very important in what I do. And what I'm doing can be called capacity computing. So I'm doing many relatively small calculations. And when I say relatively small, I mean a couple of nodes, meaning 50 to 100 cores, involved for each calculation takes about 4 to 6 to 10 hours in that order. But the number of calculations is hundreds of thousands, summing up to tens of millions CPU hours per project, basically. And the example that I'm showing here is the prediction of entirely new materials. So why would we want to do this? If you look at materials databases, current ones that we have, we know about 100,000 or so materials that exist, that have been synthesized. But if you look at the periodic table and apply some freshman chemistry rules, you arrive at billions of possible combinations. And one thing that we could do on a computer much faster than in the lab is try to test those things and see whether those materials would be stable in reality, so would be synthesizable or not. And this is one example of the things that we are doing at NREL. And in order to do that, so what I'm showing here is just like a ladder diagram of energies, and supposedly I want to predict whether a chemist comes to me with an idea of material A2BX4 with some chemical elements and ask me, okay, can you predict will this be stable at all? So in order to, and of course we are talking about solids, so we are talking about crystalline materials with well-defined crystal structures. So in order to answer that question, you need to know what the energy of that material is. So you need to sum up all the interactions that happen inside. And then once when you know the energy, you need to compare it with the energies of all other possible combinations of the same elements. And then if that turns to be the lowest combination in energy, then you can predict it's stable. And this is a slightly simplified way, but I'm trying to make a case rather than go into the details. But that A2BX4 can potentially exist in numerous different crystal structures. And this is where the one side of the problem is how do we know in which crystal structures it will exist? For the known materials, we know, but for the completely unknown things, we don't. And this is the problem that we call structure prediction. And because every structure might have a different energy, and we are interested in finding the lowest energy crystal structure for that particular composition. What do we do in calculations? We are basically solving quantum mechanical Schrodinger's equation, which is an analogous of Newton's equations in classical mechanics. And when you have a crystal structure, which is here represented by this grid, where the ions or the nuclei of the atoms sit in every grid point, then you have nuclei in grid points, and then electrons represented as these smileys are supposedly wandering around, confined in this space of the crystal. And what you want to solve is basically solve for the dynamics of the electrons, represented by this relatively complicated equation. I mean, it's much less complicated than Navier-Stokes, but it's still pretty complicated because you need to solve it for very many electrons at the same time. And they are coupled because they interact both with nuclei, but they interact among themselves. And this is what makes the problem very complex. So this problem, and again, not going into the details, this problem has been not solved, but useful approximations have been developed, and the Nobel Prize in Chemistry in '98 was given to these two guys, to Walter Kohn and John Popple, one for the development of density functional theory, which is the first principles or ab initio calculations, as it is also called in the high-performance computing community, and John Popple for the first useful implementation of density functional theory into an actual code. Okay, so what are the typical inputs and outputs of our calculations? Well, so what I input in my calculations are the positions of every atom in a crystal structure, because the crystal is a periodic system, so you need to define that only for a single unit cell, and then it's periodically repeated. And I need to put atoms in some with some coordinates into the box, and then let the codes output the total energy of the system, electronic structure, and so forth. So this is what is typically done, and then the input actually assumes a certain crystal structure. So going back to the problem that I initially started talking about, how do we know which crystal structure should we assume? The most trivial solution to this problem that I will be showing you today, there are many more complex methods to determine this, but the simplest way is to try, if I'm interested in A2BX4 chemical formula, I can go into the databases. We know 100,000 materials. I can basically look similar materials crystallizing in the same, having the same chemical formula, in how many different crystal structures they crystallize. And I can use that as an ensemble of crystal structures as my test set. And so if I can perform calculations on every one of those, I could approximate the lowest energy structure somehow. This is trivial in principle, but in practice is much less trivial. Because if you go into the databases, for A2BX4, there are about 40 different crystal structures that known materials assume. Again, you are basing everything, your results on the existing knowledge, which is an approximation again. But still, there are about 40 different crystal structures, okay? And then if you are interested in about 400 of these combinations of A2BX4, and then I didn't talk about some details of magnetic structures and blah, 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 so not going into real details, but you are easily climbing to hundreds of thousands of calculations. Independent calculations, each of which requires a couple of tens of cores, so from 20 to 200 cores, lasting in the order of 10 hours. So we are easily talking about 10 million CPU hours. And this is a conceptually relatively simple thing. Okay, we did this for the A2BX4 system. We did it for many more systems since then, but like a couple of years ago. And this took us about 10 million CPU hours. And this was done on NREL HPC. And I need to say that NREL HPC was really instrumental in achieving this. Of course, then there is the whole business about not launching all these jobs by hand, and there are some software developments about how to automatize all that, specifically for first principles or DFT calculations, and to facilitate the extraction of data, the data analysis, and that kind of stuff. I will not be talking about that, but that was also part of the work where NREL HPC helped us a lot. And then what I'm showing is the relevance of these kinds of things. So what I'm showing here is the comparison with experiments on a material that is known, so it's not new material, so it's kind of a test how all this business works. And the material is a mineral, manganese silicon 04, having that kind of chemical formula, 214. And once when you do these kinds of calculations, then you can apply some additional physical models, and then you can construct these kinds of phase diagrams of the PO2 versus, so oxygen partial pressure versus temperature, which are the typical handles that experimentalists have in the lab. It's the temperature and pressure. And then the green line or the green region is the region of stability of this material. So this is an output of our calculations. And as you can see, experimental synthesis really happened inside that green area, which kind of provides confidence that what we are doing is actually correct. This is not one example. We have many, many more of these. So this is another system, cobalt-2, zinc-4, where you can have, so again, the green region is the region of the material that we want, and the other regions are regions of the existence of other phases. Apologies for the colors. I was trying to avoid all the national flags, I know. Okay, so this is the synthesis, bulk synthesis. This is my colleagues at NREL did it in thin film chambers, growing this material, and as you can see, the agreement is good. Then this was also used, as initially I said, to predict entirely new materials. So colleagues of mine used the approach that we together developed, and while I was focusing on A2BX4 materials, they were focusing on ABX materials. They had predictions of about 50 new, completely new, never before synthesized materials, and then experimentalists from Northwestern University, our colleagues, managed to synthesize nearly 30 of those in the crystal structures predicted by the theory. And this was published in Nature Chemistry like a month or two ago. And this is, I believe, an illustrative example of why do we need HPC. So I will wrap up now and basically repeating everything that I said so far, that modern material science cannot be done without computers. We need significant computing resources. For the work that I do, it's 1,000 petascale computers is more useful than an exascale computer. So when I was starting my PhD sometime in 2005, 2006, big computers then, I was doing it in Switzerland, big computer then was like 1,000 cores or so. So relatively much smaller than what we have today. And then the question, I mean, it was obvious that much larger machines are coming. And then the whole field was kind of wondering, the field of ab initio, first principle calculations, was wondering where shall we go? Shall we pursue linear scaling methods and really do large-scale computing with large system sizes, or shall we go for doing many more calculations at the same time in parallel? And the field kind of split in two. The linear scaling is not yet there. And what we call in our field, we don't call it capacity computing, we call it high throughput computing, apparently is taking over, or at least to my knowledge is taking over. And it's relevant for experimentalists. Experimentalists really, I think, finally found use of theory, and that is really a result of a combination of theory plus high-performance computing, and I will stop here. Thank you very much.
You can just keep that up if you want. Hey, thank you guys very much. Very, very interesting. As the moderator, I'm going to take the liberty of being the first to ask some questions. So I make sure I get mine in, if that's okay. But I have a number of them, actually. But Steve, I wanted to start with you about the center. You know, I was intrigued with one of your early slides where you had the typical pyramid, and you said that some of the Office of Science supercomputing centers really focused at the tip of the spear, but that NREL was focused a little bit more on the missing middle, if I understood that. And so I kind of have two questions. One is, can those more capacity problems be offloaded onto a cloud, or do you see that happening? And then also, if that is a part of the NREL workload, how do you see that shifting in light of all the discussions that we've had here today on exascale? So we've sort of talked about the tip of the spear a lot, and yet you're talking about a center that focuses a lot in the middle range.
Yeah, that's an excellent question. So there are cloud-like applications that are certainly done at our facility. And when sometimes they involve proprietary information or work with a industrial partner, they would prefer that that be protected within NREL's firewall. So while some of those calculations can be done in a cloud-like environment, they would prefer it not be done in the cloud.
Got it.
So that's one avenue. The other, when I look at sort of the role we play, and it's not just about the computing, and there's been a conscious investment by EERE in expertise to work closely with the domain specialists in the area of modeling and simulation that's important to these specific domains to get them started at all. Right? And part of the notion is not to be duplicate what's done by the leadership class facilities, but to get folks started and to graduate them as the field matures, as the problems mature, as they gain comfortability, as the models that they use advance, and to graduate those so that they use the leadership class facilities that the Office of Science is providing.
Do those users have to have EERE funding, or do they just have to have a project that is aligned with the EERE mission area?
So there's priority given to EERE-funded projects,
Okay,
but it's not a requirement.
not a requirement. Okay, great. Do we have other questions? Oh, I'm sorry, did you?
Vlad, did you want to say anything about cloud computing?
Well, okay, I'm not really a specialist for cloud computing. I guess the things that I'm doing, because they still involve using in the order of between 50 and 100 cores, which have to be connected with the fast network. We use quite a lot FFT to do things that we do. I'm not sure how can that be implemented in a cloud. If there is a cloud that provides those kinds of capabilities, that you can have a cluster of 100 cores somewhere, then probably yes, but I'm not aware of that.
Do we have any other questions from anyone out in the audience? Great, right here, and then over here to Vijay.
This is more a point than a question. John Popel got the Nobel Prize Award for computational methods in theoretical chemistry, not just DFT, the wave function methods as well.
Yeah. Okay. I agree.
Great. Vijay?
Quick question. I saw a slide in which you said that the behavior of a single turbine is quite different compared to behavior of collection of turbines in a wind farm, right? And I imagine part of the implication was that it can lead to larger failure rates of blades when they are in a farm. And so my question is, does the lab consult with people who are operating building farms, and are we in a position to simulate a collection of 50 to 100 wind farms within a given location and so forth? Where is the state of the art in that? That's question one. And two, is there any work going on vertical turbines as opposed to these ultra long 50-meter blades?
Okay, let's see. So let me just clarify. The failure rates are mainly seen in the gearboxes and bearings. I don't know so much about the blade failure rates. So this is where I'm not a domain expert. I'm growing into one, but I'm more on the, Navier-Stokes is my domain more so than, actual blade failure modes. But you are seeing significant failure rates.
So let me ask you this. If you're seeing in gearboxes,
Yeah.
is it tied to greater density of blades? Windmills, greater density?
Right, so the whole system is going to be experiencing,
Right, yeah.
when you put the turbine in the wind farm, you might have seen it, everyone is living in the wake of another turbine, effectively. And that brings much more oscillatory forcing to those systems. And so they see a lot more related oscillations, force oscillations that a single turbine would not see. So that's basically what I meant by that. Now, your first question was working with, how would you say that again? Basically, like it.
Working with people who are building wind farms, 50 to 100 wind farms in a given area, how good is our simulation ability there?
it's not good, right? The models that they're using to design the wind plants right now, there are very few people who are doing the kind of simulations that I was showing in designing the wind plants. And the high fidelity simulations at best will only be a point check, right? They'll basically come up with the design and they can basically do a point check because the simulations are so expensive. So they use much lower fidelity models than the design of the wind plants, linearized type models for designing the wind plants. And then when they're built, they often underperform, right? Because their models were not good enough. So the state of the art in actually affecting how the wind plants are designed, HPC is beginning to help, but it can do a lot more.
So what's the limiting factor? Is it capacity to compute, or is it the physics?
Both, right? I mean, the calculations are so expensive to do if you're going to, the state-of-the-art calculations, like I was trying to get at, they're petascale type simulations, and you're going to be able to get a 30-minute simulated time over a couple of weeks on Mira, right? So that's of great limitation using it in design. That kind of calculation, in my mind, its purpose is really in understanding the system and affecting changes in the low-order models that are actually used to design the wind plants.
Between NREL and northern European countries such as Norway or Germany, or where there is a lot more. I mean,
Oh yes, yes. For example, the DTU guys seem to always be in some number at the NWTC and Germany, and you know we have a lot of European collaboration going on for this problem. Yeah.
Yeah, so we, so wind turbine data is, and the failure rates are sort of closely held company secrets, if you will, right? So if probably if you go maybe a mile south and a couple miles west, that's the National Wind Technology Center. So there's a handful of utility scale turbines there. So when Mike talked about NWTC, it's just, I think it's just over the hill. You just can't see them, but they're there. So we formed a gearbox collaborative. We collected gearbox failure data from a handful, and I don't know the exact number, I think it's order a dozen owner-operators of wind farms, and try to find root cause analysis of operating conditions and failure modes to go back and then update both the operating conditions or the control system, the control sequences, and to help the industry improve to reduce the mean time to failure. And some of that came back to, well, our turbines are living in significant turbulent regimes due to the wakes and the interaction of the upwind turbines. How can we steer the wakes by adjusting the pitch and the yaw of the blades? What the video that Mike showed was showing the steering of the wakes, which is some of the results of that, of taking data of failure rates. So it has a multiplicative effect. Both it's reducing the cost of the energy by improving the energy capture, plus it's putting the turbines in a more stable environment, so they're not going through the chop of the upwind turbines, which again puts stress on the gearbox. And then to answer your second question about vertical axis turbines, the energy capture potential of a turbine, whether it's vertical or horizontal, is proportional to the swept area, right? And you've got to get your turbine into the right wind regime. So you actually get the nacelle up. The turbines we have at NWTC, the nacelle, the gearbox sits up about 80 meters. And you're into the bottom of the planetary boundary layer where you get very stable night flows. If you wanted to be able to take advantage of that with a vertical turbine or a vertical axis turbine, it sort of spins like this as opposed to like this, they have to be much larger systems. So your energy capture potential per installation is much smaller unless you start packing them like trees, and then they have greater impacts on each other. So the state of the art right now really is 3-blade horizontal axis turbines. And if you go offshore, they're just massive 10 megawatt systems are being deployed.
I know we have a question in the back here, but while we're still on this topic, I had one just so we don't lose the thread. It's kind of related to what Vijay was saying. Mike, you're doing this modeling now of farms to understand the vorticity between the different, the individual turbines and how they're having an impact. But if this is so sensitive from a company perspective, who funds you to do this? Is it all done on like a work for others from a company and it's proprietary? Or does this data then somehow get back out to industry so that industry then can use it to make adjustments in how the farms are set up? Or is that question too sensitive?
No, that's fine. That's fine. Let me try, Steve, before I hand it off. Right, so everything we're doing
And I
is
haven't
open
forgotten the
source.
person back there.
I mean, we do have a work for others part in our portfolio, but everything that I'm talking about is all open source, and that's from the data that is gathered in the experiments, the simulations that we're doing, to the software that the Department of Energy is trying to develop. It is all meant to be open source. And then for my part in this, or for our part in this, I mean, we want to deal with open source systems to demonstrate the capability. We want those capabilities then influence what the industry itself is using, right? So we're trying to come up with the ground truth simulations and the state of the art in the computational methods for solving the systems, and we want the industry to take those things and to push the process. And then for our validation, for example, we have a 3-turbine wind farm down that's being put up in the Swift facility in Texas that Sandia is putting up. So part of our experimental validation of these systems is to work with that open source system.
I see.
So, you want to add anything to that?
Yeah, so the Gearbox Reliability Cooperative was funded by the Department of Energy Wind Program
Okay.
to fund lab resources, staff time, and sort of capabilities in computing to anonymize the data so that each company could see its data and everybody else's, but you knew which was yours, but you couldn't identify anybody else's directly. So it was supported. The companies came because they realized that they didn't have enough data all in their own to be able to find the whole problem, to find that needle in the haystack, but collectively they could.
Got it.
So DOE supported the gathering of the tribes to get together. NREL was the trusted holder of the data without sharing whose data was which, associated with which particular installation. And then it was shared. They all could see the data, but they didn't know whose was which.
Cool. Very good. Now, I think we had questions in the back. Someone else had a mic?
Yeah, so actually Susie stole my question.
Oh, sorry.
But I kind of have a follow-on. So are there issues around intellectual property, and do you have a kind of coordinated intellectual property agreement that your industry folks sign?
I don't know what the intellectual property arrangement was with the gearbox reliability, but for typical collaboration where if it's a funds-in cooperative research and development agreement, if it's a funds-in CRADA, then the company owns its pre-existing IP, joint IP is governed by whatever terms are negotiated within the CRADA agreement.
So you're signing CRADA agreements even if no real money is flowing from companies?
So there was the arrangement. I don't know what the arrangement was done with the Gearbox Reliability Cooperative that was set up. But I know the intellectual property will depend on the terms of the specific CRADA agreement.
Yeah, okay.
Question over here?
I'll maybe just follow one more little bit for that. One of the things we're doing right now is we're working with Siemens, and that did start under a CRADA, and Siemens has been great on this one because we're basically doing a validation of our turbine models with the big 2.3 megawatt Siemens turbine that's just, as Steve said, over the hill from here. And we'll be publishing that data. We just need to mask the data in the sense to make it non-specific. So just another example of what we're doing with the industry there.
Back here,
Just,
Doug?
yeah, just a comment. The ECI, the DOE ECI project can and likely will support applications that need ensembles as opposed to, one big honking simulation. The point is we're seeing lots of need for sensitivity, optimization, uncertainty quantification. So there's, those sorts of workflows absolutely can and will be supported.
Great. Thank you, Doug.
Do you worry about taking too much energy out of the motion of the air? I mean, if you stop it all, it's not going to rain in Kansas anymore, and they're going to be irritated.
It's a fun question. Yeah, we are. It's so this is If you have the wind plant centric view, you can look at your weather forcing as a one-way forcing. If you're a farm that is sitting behind a very large wind plant, then you are very much interested in the two-way coupling aspect. So part of this mesoscale, microscale coupling initiative that I spoke briefly about, it is interested very much in the one-way coupling of forcing the wind farms, but there is also great interest in the two-way coupling. What does a wind farm do to local weather patterns? So definitely. Julie Lundquist is the name that comes to mind up at CU Boulder, who is very much looking at that measurement point of view from out in the field measurements of changes in precipitation in particular in the vicinity of large wind farms.
But if you think of the wind turbines, a wind farm as being a small, almost a small mountain, right? Because it puts a drag on the bottom of the planetary boundary layer. So it's going to slow it down. You will alter everything from precipitable water to freeze-thaw cycles. Right? So if you know what they are, that could be to your advantage. Right? You could use it strategically, not just, holy cow, what are we going to do? Right? So knowing how close you can space them, what the impacts are, you certainly don't want to put in turbines in Kansas that turns Iowa into a dust bowl. Right?
One more interesting point on that is, what if you build a wind farm and then someone builds a wind farm right in front of you?